We're going to forget that there are electric and magnetic fields totally. And we're going to simplify light in a way that'll help us sort of see what macroscopically happens when light interacts with other substances. So what we're going to do is this. First of all, we're going to define something known as wave fronts and wave rays, which will be our first step towards simplifying away the waves themselves. So wave fronts indicate the crests or the peaks of the wave. You can see them denoted as these green circles over here. There's some source of light at the middle, and light is going out in all directions. And you might imagine that at the locations of the green circles, we have peaks in the wave. So in other words, if we were to look at this from its side, how can I draw this? Oh, everything is terrible. So let's imagine that maybe there's our source, and then we have light just in one direction, just to simplify things. Then maybe we would get something that looks like this if we're dealing with the electric field. This is one green line, that's another green line, that's another green line, and so forth. Okay? Let's change the color to match a little better. Those are the wave fronts. So looking at the wave propagation from above, you're looking at the place where the peaks in the wave exist as they sort of spread out in all directions. Good so far? Okay. So you can see it's almost like we took this three-dimensional wave and we're starting to flatten it. We're still noticing that the wave is there, but we're ignoring most of its structure. Once we have that, you'll notice I already drew a blue arrow there. If I draw a line that's perpendicular to the wave fronts, we call these wave rays. Perpendicular to the wave fronts are the wave rays, and they indicate the direction that the wave is traveling. So you can see we've drawn a bunch of rays just traveling all directions out from this particular source of light. Everything that happens sort of in the remainder of this chapter and in the upcoming chapters about light are going to focus on rays of light, which is just like imagining that light travels perfectly in one direction. Okay? So what we're going to do is even simplify this concept further and say that if I'm far enough away from the source of light, you might imagine that, well, adjacent rays are essentially traveling parallel to each other. This is kind of the whole idea of the flat earth stuff again. Yeah, right. If it's big enough, it appears flat because you can't really tell the curvature is there. So here we have rays of light that are spread out so far that parallel rays of light don't appear to be spreading anymore. They essentially appear to be parallel, okay? You can't tell that they're all spreading out from an individual source. So, let's see. We need a planar wave fronts. Wait a minute, is that on the other side? Let's put a little note here somewhere. If far enough away from source. Adjacent rays are essentially parallel. That's all you need to know from this slide. Okay, we're going to be dealing with rays of light that are essentially traveling straight because we're going to be far enough away from anything that's making the light, which allows us to do things like the law of reflection, which we already talked about. So here we have an incident wave, which is represented by a ray, and it reflects at exactly the same angle that it hits a surface and reflects off of it. We did all of that. I don't think there's anything terribly complicated about that, but we didn't talk about some of these other diagrams in detail. How do we see reflections in a mirror when I have an object that's all sort of spread out, and every little point of that object has light that's coming off of it and potentially being reflected by the mirror? Notice they are using the law of reflection here just over and over to sort of recreate what you see in the mirror. So you might imagine there is some light that's leaving the bottom of this flower. There's some light that's leaving this point. There's some light that's leaving this point, and this point, and this point, and this point. I'm getting tired of doing this, and so forth. Every little piece of the object has some light that's reflecting off of it. And it's traveling up to the mirror, and maybe I'm off to the side and I'm only an eyeball, which is a little sad and depressing. Whatever I'm seeing is the result of light from all different points of this object traveling to the mirror and then reflecting off of it according to the law of reflection. Notice they are drawing just 4 light rays. So you can see from this point, you might imagine that, well, there's a ray that hits here, reflects using the law of reflection to my eye, and if you just take a really close look at that, let's zoom in, well, you can imagine a perpendicular line here, the angle in equals the angle out. Seems like that's working. If we imagine another ray that's traveling a slightly different direction from that, you can see it bounces using the law of reflection as well as all of these others, and I don't know why things aren't keeping up with me. Come on, pointer, you can do it. Okay? All of these little incidents with the mirror are following the law of reflection, which leads to all of these various light rays hitting my eye. Okay? Our eye assumes that whatever I see, like that light ray was just traveling straight from some object. It doesn't like build in an idea that like, ooh, maybe it curved around a corner. Well, first of all, it doesn't do that, and also our eyeball knows that, okay? So when I trace this thing back and imagine this light ray that it's received by the eye has a source that's directly behind it, you can see it traces back to an image that we see in the mirror that's exactly the same distance away. And if we trace this one back, it goes back to another point right at the top of an image of the flower, and so forth for all of these. All of the rays that hit our eye, we imagine coming from some source that's directly at the other end of that ray. Our eye knows nothing of this reflection that happened in the middle. So we see an image of it that's built behind the mirror or in the mirror that's not actually there, okay? All of it's happening because of multiple instances of the law of reflection sort of over and over building up that image that we see. All of this detail we don't need to worry about right now. More of that's going to come back in the next chapter. At this point, we're just talking about the law of reflection and how it applies. So, a few questions. Let's see. Can you think of a reason why, if I'm watching the moon over the ocean, I don't see a perfect reflection of the moon, but often you see like sort of like a trail reflection that's kind of coming, leading from the moon itself or directly under it, all the way to where you are. Which one of these reasons might cause that to happen as opposed to a nice mirror reflection? Some of these are ridiculously ridiculous, don't you think? It should be, shouldn't it? Or should it be? How do you know you have the right answer? What do you think is the answer? Yeah. So maybe it's sort of a Goldilocks thing, and the atmospheric conditions are just right. You gotta love that. No, nothing here really makes sense except for the ocean being wavy, okay? If you imagine there's just a bunch of motion in the ocean, every time that light from the moon hits, it has to follow the law of reflection. I'm going to get reflections in a bunch of different directions because the perpendicular to that surface is a bunch of different directions, and that sort of messes things up, all right? Let's see. Taking a look at this. There is an observer at point O, okay, and a light source at point S. It hits the mirror at point 1. Where would the image of the source be located? Please don't think too hard. It certainly appears that the image would be located at 2, because if I trace that light ray back, that's where I would observe that ray to be coming from. Okay? Number 3. Oh, look. Apparently, everyone always wears white and blue. It's just a thing. It'd be interesting, though, if we zoom in and it's actually the face of one of those dudes from before, and they just reuse faces in different ways. Is this even the same person? I don't know. Wow. This one's faded by comparison to that one. I don't know. That's just weird. What do you think?
It's a mirror.
It should be, but I don't know. I think this is just a creepy version standing on the other side staring back. It's a window, not a mirror. So So what do you think? You stand in front of a mirror. How tall does the mirror have to be so you can see yourself entirely? Do you have any experience with this? Kind of want to try it? I don't have a variable length mirror. I don't know that anybody does. It'd be kind of odd. The rays of light that are drawn there should be able to lead you to the answer, believe it or not. There's actually helpful information on the screen. That was good timing. Any thoughts? Any explanations? Anyone want to guess an answer and tell me why? 1? 5? 3? Okay, let's just pick everything. I like 1, 5, and 3. It seems like it would be one of those, right? Not some sort of random in-between answer. So which one? 3? Can the person see their entire image in this diagram? Certainly seems like it, right? And it would also appear that that mirror is half their height as well. So 3 is the answer. And now I know all of you want to go to the mirror store and try this. Question over there? If you move backwards, is it going to change anything here? You could move back, but it's all about the size of the mirror. There's a limitation there. If the mirror is only this high, I can't really go back far enough. There's going to be a problem with the rays. What if we use a series of 3 mirrors? One on all sides? Here's the key. As I back up, the rays are still pointing the same directions that they are. It's just the angles are changing. So, does it depend on your distance from the mirror? The answer is, well, no. And it certainly doesn't depend on the person. That'd be kind of odd. I can see my entire reflection. Can you? No. A vampire would be a problem. Let's see. You hold a hand mirror 1/2 meter in front of you and look at your reflection in a full-length mirror 1 meter behind you. I'm confused already. How far in back of the big mirror do you see the image of your face? I glanced at this problem earlier when I was reviewing this, and for some reason I thought it said, how far in the back of the mirror do you see your big face? And I was like, that can't be right. It's just a little too close there, and at a glance, I was like, I don't know if I can do this problem. It's kind of mean. We're not worried about how big the mirrors are because I'm not concerned about the vertical height. We're just trying to see where we see the reflection of the face. Yeah. Say it again. Uh-huh. No. At this point, let's talk later. Yeah. If you look at the rays, you can kind of add up what you're seeing there and see that it's exactly half the height, but we'll talk about it later. I like this question. And 2? So if we imagine this space back here, like this is kind of like the virtual space inside the mirror, like if you want to think about it that way, where back there is the face? what are you going to see in there? You're going to see yourself, first of all, right? Oh, I don't know if I can do this. So there's like a head, kind of, and then like, there, the rest of the person. Yeah, that's some good art. Yeah, the head is not disconnected, so I drew it that way. Yeah, so how far behind the mirror are you going to see the back of you? That should be 1 meter, right? Uh-huh.
Too many words.
Yeah, there is too many words. And then you're holding, let's see, this other mirror. Ooh, how far back is that? That's another 0.5 meters. So it says, how far in back of the big mirror do you see the image of your face? Whew, this is a bad question. So where are you actually seeing the face is somewhere like back here, right? Which is another... Whew. What a terrible question. It is weirdly worded. Are you in agreement and you're just stunned, or you're like, wait a minute? No. Yes? Lots of confusion? Everything we see on that side of the mirror has to happen over here as well. Okay? But also keep in mind, this image of your face in the mirror isn't where the mirror is, right? You see that behind or inside the mirror, right? They kind of drew it in a weird way. You're actually seeing your face reflected like that same distance back. So what's the answer? But looks a whole lot like 2 meters. This feels like fluids all over again, right? You know, during the fluids lecture, there was a lot of, wait a minute, I don't like any of this. And now this is your question. Like perpendicular or back to back like this? Yeah. That's where you see the other dimensions. We'll maybe get to stuff like that. We'll keep it simple at this point. Uh-oh, that's not good. Huh. No. My watch thought I took a fall. Oh, I slammed my hand down. Yeah. Interesting. I did not take a fall. You do not need to call emergency services. Does anybody have any follow-up questions on this one? Are we in agreement with the answer at this point? I think for the most part we are, which gives us just enough time to talk a little bit about refraction to help you out going forward. Boo? Do I hear boo? Who booed? I don't know. So once again, actually, I put this in here just because it's fun looking, but we're not actually going to do that work. We don't need to. We talked about the index of refraction, which is all based on how much light slows down from the speed of light in vacuum when it's in other mediums, all right? We talked about Snell's law, and I gave you this little brief example sort of thing that sort of helps you see where these different angles are and the different quantities are. What we didn't talk about is any of these points below. Notice, the first one says that when a ray of light enters a medium where the index of refraction is increased. If the index of refraction increases, this is because the light travels slower in that material. And with a good bit of work, which involved like this thing on the previous slide that I said we're not going to derive, so don't worry about that. It turns out that the ray will be bent toward the normal line. That's the opposite of what I drew here. So if we're going into a higher index of refraction, you can imagine instead of the light continuing straight, it's going to get closer to the normal line. It bends inward as the light slows down. Okay? The opposite happens if it's going from a medium where the index of refraction is decreased, if it's less. In that case, the speed of light is increased, and you'll have the case, like I drew above, where the ray of light bends farther away from the normal line. Okay? If you wanted to, you could use Snell's law and just plug in some numbers for Ni and Nt. And it's pretty easy to quickly see that this is the trend that's happening. I just wanted to point it out because very often you're working homework problems, it's going to ask you related questions, or you're going to have to do such things. It's easy to just like remember that these two things are what's going to happen and which way the light's going to bend will be helpful, okay? The third one there is no change in the direction of propagation if there's no change in the index of refraction. So like we said the other day, even if it's two different materials, if they happen to have the exact same index of refraction, it's almost like they're the exact same material. In other words, from the light's perspective, they're exactly the same. They're identical. The light's going to keep traveling at exactly the same velocity, and it's not going to matter. And then the last one, if it travels directly along the normal line. So in other words, if the light were coming directly down this line, perpendicular to the interface between the materials, if I could talk, nothing happens. There is no bend. It would just continue directly through. And this time, you could plug in 90 for the angle of incidence, and you'll see that, 0 for the angle of incidence, and you would see that you end up with 0 on the other side as well, okay? So I only put those there to just help you have a list of things to remember as you're working problems. All of those can be shown using different numbers and Snell's law if you wanted to, okay? Question in the back. The speed of light is c in a vacuum. So we're dealing with cases where it's always something less. So if you imagine it going from, say, water into air, in that particular case, it travels faster in the air than it does in the water, but all of it is less than c. Good question. The next slide I have is an example that takes a long time. See that? There's a lot of stuff that's happening there. We've got 2 minutes left. I'm going to write quickly. You're going to be extra confused, and that's going to be sad, so I won't do that. We'll finish this chapter up on Friday. Goodbye. Goodbye.
So, let's see. Snell's law. We got the equation. We didn't do an example, which was the next slide, and I said this was a bit of a lengthy example. It'll take some time. It'll also introduce a new topic somewhere about halfway through. So take a look at this thing at the bottom. Imagine we're looking sort of down on the top of a piece of glass that has some thickness. We're going to take a beam of light and shine it into the side, and then we're going to look down inside the glass and sort of see how it bounces around on the different surfaces, okay? So let's say that we have air on the outside, and this is glass on the inside. And we're just going to use 1 as the index of refraction of air. So N sub A is 1. And let's see, does it tell us up there anywhere the index of refraction of glass? I don't see it, so I'll have to tell you what that value is. Which number are we going to use? Oh, actually, they did give us enough information to find it, though, didn't they? It says that the speed inside the glass is 59.3% of the speed of light in a vacuum. So we can use that equation we had, N is equal to C over V, to find the index of refraction of glass. So this will be N sub G. So in the numerator, we have C. I'm just going to leave that as C so that we can keep the bottom velocity in terms of C, since they gave us that as a percentage. So that's going to be 0.593 C. And then the C's cancel, and somebody could tell me what the reciprocal of 0.593 is, perhaps. Like how you all look around like, I've got a calculator here somewhere. Like, I don't know. I feel like it's almost half pretend, though. Like you're looking around while you're just faking it. Like, oh, I'm going to find my calculator while somebody else does. You've got it already? Sure, I hope so. Why not? Does it round to anything higher? Let's just go with 1.69. Why not? Somewhere in between what's happening there. Notice there is no unit for index of refraction. It's velocity over velocity, so all the units cancel out. So 1.69 for the index of refraction of glass. So let's start with this first interface. We have a beam of light coming in. It's hitting the side of the piece of glass, and it's going from air into glass. Okay? First step is a normal line. So let's start by drawing a little normal line here. Okay? That's not vertical or perpendicular at all, is it? Ooh, look at this. Look what's on the next slide. I'm going to use this one. This one's bigger and better. Perpendicular line. They gave us this value of theta 1. Is that the angle I'm supposed to be using? No. That we're supposed to use the complement to that, right? So I'm going to call that theta 2. So instead of having incident and transmitted or refracted angles, I'm just going to give them all subscript numbers because we're going to have a bunch of different angles as we work through things. So as it goes into the glass, is it going to bend closer to the normal or away, farther from the normal? Speed of light is going to drop, right? It's going to be going slower. Look back 2 slides. Does it go closer to the normal or farther away when the speed of light drops? Closer, right? So it's going to bend in at least a little bit, and I'm just going to make it, oh, that didn't bend at all. I'm trying to make it go this way a little bit, but I still want it to hit side B, and you can see I'm running out of space there. Okay? So it's bending inward at least a little bit, and I'm going to call that angle theta 3. So we're going to start by trying to find the new angle as it enters the glass. So we'll use Snell's law for that. So let's see. N sub A times the sine of theta 2 equals NG times the sine of theta 3. And we're going to solve that for theta 3. So let's see. Theta 3 is going to be the inverse sine of what? NA sine theta 2 over NG. And at least at this time, I'll plug the numbers in to make sure we're all on the same page. So N for air is just 1, so we might as well write that down. Theta 2 is going to be what? Look back at what was given. They told us that theta 1 is 57.8, so 90 minus 57.8 is 32.2. And then in the denominator, we have 1.69. So what do you get for theta 3? Anybody? Thank you for coming today, by the way. Yeah. My wife said, like, why are you even bothering going when, you know, it's all on video? I was like, well, I have to go to make the video. She's like, that's a good point. Yeah. 19.05. Are you sure it's correct? Are you double sure? I'm not sure either. Hold on, I'm looking for the number. I've got something slightly different. It's really close to that, though. Let's make sure that I wrote down all the right numbers. 1 over 1.69, sine of 32.2, inverse sine. 18.4? I do have 18.4. Just double check and make sure everyone's getting the same number. So now, this light is going to keep going this direction and eventually run into side B. Okay? So we have another case of refraction at this point. Now it's trying to go from the glass out into the air. So let's once again draw a normal line. This angle I'm going to call theta 4. And if it's going from a higher index of refraction to lower, which way is it going to bend this time? It should bend farther away. Oh, so kind of out that direction. Let's call that theta 5. Theta 4 we can directly find just by using a little geometry inside there, right? So I've got this right triangle, and we know theta 3. So theta 4 is going to be 90 minus theta 3. So let's go ahead and do that. So let's see, theta 4 is 71.6. And then we'll use Snell's law again in an attempt to find theta 5. Okay? Is everyone still doing okay? This makes sense? Snell's law, fantastic. You love Snell's law, right? Snell's law is a beautiful law. Okay, just stare at me. I feel like you should all be a little rambunctious today, like excited. It's almost, is it the rain that's got you down? Are you just tired? It's all kind of all the above. Are you going to leave here today and then just collapse into a pool of Netflix? Maybe a little bit. Okay, I got you. So let's use Snell's law once again. I may collapse into a pool of Netflix as well. That sounds like fun. N sub g this time, because we're starting in the glass, times the sine of theta 4 equals n air times the sine of theta 5. We'll do the exact same thing again to solve for theta 5. So theta 5 is going to be the inverse sine of ng sine theta 4 over na. This is tedious a little bit, isn't it? No? Because it's straightforward, maybe? Yeah, but a little bit tedious. Somebody punch that in your calculator and tell me what you get. You don't have the answer already? What? You calculated something a few minutes ago, though. I bet it does if you put it in landscape mode. I bet you. Cinch? Now, if it has hyperbolic inverses there somewhere, it's got to be. There you go. It's there somewhere. It's got to be. Oh, never mind. Just throw your phone away. It's broken. Does anybody have an answer? 1.69 sine of 71.6 inverse sine. Oh, finally. We can be done early today if you people calculate faster. Did you find the inverse sine? It is on there. You're using an iPhone, right? I saw an apple on the back. I use a different calculator. I don't even know if I have the regular one on here. You found it? Okay, good. Yeah, I don't have the regular one installed. You got error? Error? Error. Yeah, that's the correct answer. Ooh. Oh, that was unexpected, right? This equals error. Yes. There's no joke here. I would say error. That's true. It sounds like my kind of joke, doesn't it? The answer is error. Let's move on. That's exactly what we expected. What in the world happened then? Question. Went into who? Side C? Actually, we didn't run into side C. That's a good thought, though, because it kind of looks like it wants to. But I was told in advance of this problem that it does hit side B. So that's going to happen. How about this? Or you have an answer? It is total internal reflection, which is something we haven't talked about yet. I'm just going to tell you at this point, total internal reflection happened. Or, as I wrote it, total intertal. Something. I don't know. Total internal reflection occurred here, which means that this thing that we drew on the outside actually didn't happen. The light does not leave the glass on this side. In fact, all of it just reflects. It bounces off using the law of reflection over to side C, but no light exits. If we were to put our finger outside on that side, we would see nothing pass through, okay? We're going to come back and look at that phenomenon right after we finish this and a couple of other multiple choice questions, and I'll explain what's happening there. Just keep in mind that the equation has told us something weird went on. There is no theta 5. It doesn't exist. The equation gave us an error because there literally is no theta 5. There is no angle out there to measure that light, okay? So let's move along, once again using the reflection. So we know that this is going to bounce, kind of, if I can get this right. I don't know. I need these angles to be roughly equal. Let's call this theta 6. The law of reflection says that theta 4 and theta 6 should be the same. So we can quickly jump to the next part. So theta 4 equals theta 6 equals 71.6 degrees. Which brings us to this last side, and then I think that's probably a good place to stop the problem, because we could just continue this, right? Like, I mean, there's no reason to think that this isn't just going to be like, we're, blah, 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 and we could do this problem forever. But alas, we don't have that kind of time, okay? So I want to see what happens at side C, and then we'll call it quits. So let's bounce this light off after we draw a normal line. And we could say that this is going to bounce off sort of this direction. And I need to find theta 7 that's hiding inside there. So this is theta 7. I'm going to zoom in. Ooh. Theta 7. How can I find theta 7? What a mess we have going on. It's not a right angle. But the geometry is there. There's enough. I'll give you a second to stare at it some. Notice that big alpha up there. They gave us another angle. That's this. And I forget what they said that was. 78.2. Now can you get there? See the steps? Did you follow that? So we have this one, and then this connects to a straight line over here. So this is 180 minus 78.2, whatever that is. 91, no, 101.8? Yeah, you sure? Okay, why not? Let's write that in. So this one here is 101.8. Whew, and now what? We can find this one, which is 90 minus 71.6, right? So that's going to be 18.4. Which means that now I can find this one, because I still have a triangle there. So 101.8 plus 18.4 plus whatever that angle is has to give me 180 degrees. Right? So somebody tell me what that number is. I don't feel like doing that in my head. Help. Help. 159. $180 minus 18.4 minus 101.8. 59.8? Okay, sorry, I thought you said 159.8. No, I was like, that can't be right. So this is 59.8, which means that now we have this right angle, and we can find theta 7, right? Oh, which is going to be 30.2. That should get us there, 30.2 for theta 7. I think that's just overly complex, perhaps, for this problem, but I don't know. There's enough information in there to get to it. 30.2 is that last angle. So once we have that, now we can say that this is going to bend away from the normal even more, because it's still from glass out into air. So we can say that in glass times the sine of theta 7 equals in air times the sine of, I don't know, theta 8. Why not? And now we can find theta 8 using the exact same approach. Somebody tell me what you get. Never mind, I don't want to wait. I've got 58.2. Okay? A couple of applications of Snell's law, one of which, well, kind of failed there in the middle because of something else. Okay? Snell's law itself, I don't think, is overly complicated. I think you can handle it, yeah. Question in the middle. You can find that it's going to be total internal reflection this way, or you can use an equation I'm about to give you so that you can know in advance whether that's going to happen. Okay? Anybody else? Yeah?
So in this case, so when it goes onto the side B, are we saying always gets refracted or it has refraction?
Both are happening. Typically at an interface, both is going to happen. Like we could go back here and imagine that some of the light actually goes that way. At an interface, you're going to get some of both, and the light intensity is reduced for whatever's remaining in both directions. Yes. Yep. Okay. So let's leave this problem. I want to ask you a few quick questions, then we'll talk about total internal reflection, and then we'll be done. Okay? So take a look at case 1 and case 2. From air into two different mediums, in which case 1 or 2 is the light traveling faster? Somebody's notebook is up here. Wonder what it says. Scalars and vectors. Ha ha ha. Could this be someone's notebook from last semester? Oh, it didn't last long. I think they dropped. That was sad. They made it through like the first lecture and the first homework, and then it just ended. All of them are empty after that. Huh. Yeah, that's about it. Well, I'm sorry, notebook. Nobody wants to claim it? It's not any of yours? No, I didn't think so. You want it? You can't just take it. It could be somebody's, like they actually own it. All right, so which one is the light traveling faster? Should be the one where it doesn't bend as much, right? As if it bends more toward the normal, that means we have a greater reduction in speed. So that means medium 1 should be the one where it's actually moving faster. So we'll say less bend toward normal. Okay? Can you take that and make any assumptions about 3 different materials? Ugh. Notice this time it's not asking about the relative speed of light in the 3, but kind of the converse of that, the relative index of refraction for the 3. Think it through and see if you can rank them. You all are a mellow bunch today. Just chilled and relaxed. I feel like you're kind of already on break. It's not a hyper type of feeling, though. It's just like you're just easing right into nap time for a whole week. You're hoping that maybe I would talk slowly today and just help you relax. What? You want me to speed up and not be relaxing? Go to sleep. Go to sleep. I'm not going to sing anymore. So let's think about this sort of frontwards first. In which medium do you think the light is going fastest? Why 3? It moves the furthest away from the normal. I would agree that it's going the fastest here. Which one do you think is the slowest? 2? Are you sure? Okay, I think I would agree with that. The one that doesn't move from the normal as much? If it bends away from the normal in that medium, it's going faster than in whatever it came from. So if it bends more and more, then the faster it must be traveling in that material. So apparently it's moving way faster in 3 than it is in 2. Because of how far away from the normal it's bending. And 1 is camped out somewhere in the middle somewhere. So what does that tell us about the 3 ends? Should be, N2 is going to be the biggest, and then N1, and then N3. N2, N1, N3. Is that an option? Oh, well, I just screwed the whole thing up then, didn't I? Let me go double check. Am I thinking about this right? Where are the answers? None of the above. 3. Oh, I just did it backwards. Somebody help. Two, greater than 3, greater than 1. It looks like I've got these two flip-flopped. Let me let y'all think about that for a second while I do the same. 1 and 3 are flip-flopped. Oh, wait a minute. Hold everything up. That was 1. Hold on, am I looking at the right problem? Then we did the second one. Wait a minute. There's 1. Ha! Look at this. I was right to begin with. The answer is actually none of the above on this one, just to throw us all off. That's just mean. I was looking at the wrong number on the screen. So that one is actually correct. N2 is greater than N1 is greater than N3, because you can think of that as sort of backwards from the way we think of the velocities. Okay? Yeah. Yeah, so here, instead of going directly through, it bends this way, so I could immediately say that 3 is going to be faster than 2, because that's bending away from the normal. Then from the top 2, since it bends toward the normal, we could say that 1 is faster than 2. And then you can put those together to see how they rank relative to each other. By the way, a little cheat on this one. Remove number 2, like mash 1 and 3 together, and it's kind of a shortcut to getting to the answer. If you sort of imagine that I had 3 and then the light just sort of did this, then that tells you the relationship between 1 and 3. Just imagine 2's not there at all, and it goes directly from 1 into 3, and it follows the path that we have drawn in 3. The exact same answer results from that. Okay? Which brings us to shooting a fish. I know, no one should shoot a fish. Sounds terrible. Plus, I don't think that's any way to catch a fish, even if you want to catch a fish. It just seems terrible. So if you wanted to shoot a fish with a gun, should you aim directly at the image of the fish, the thing you see, or should you aim slightly above or slightly below? We're assuming the bullet from the gun can actually travel along a perfectly straight line. We're going to assume that gravity doesn't have a great impact because it's moving so fast and not going a great distance, okay? So just based on what you see, where do you think you should aim? Why above? Both of you are saying above. Why above? Refraction happens to light, though, not to a bullet. We're assuming the bullet can just keep on going. It is going to go slower, yeah. What do you see? Thinking about what you see. The image is shifted. That's what's going to help us. So you might imagine that light from the fish, because all fish emit light, apparently. So light is reflecting off the fish and like going up here somewhere. How does it get to my eye? If it's going from a higher index to a lower index, it must do something kind of like this. Okay? That is bending away from the normal line. So that means when I look in that direction, I'm seeing an image of a fish that I think is right here, fish. But it's not actually there. Okay? So this is the image of the fish. So everything is a little backwards than what you think, huh? So instead of shooting exactly where I see the fish, I know that because light bent as it went from water into air, The actual fish is underneath that. So you need to aim slightly below. Ooh, that was unexpected, right? Okay? You're not seeing the fish where it actually is because the light refracted at the interface between water and air. Gotcha, didn't I? So what if we tried to shoot a fish with a fancier gun? Look, now we have a laser gun. Someone put some time into that one. Look at that. I know. And back when we had wires, the wires looked like this, right? And then they draw this laser gun, supposedly. Now, a laser gun is shooting a beam of light, which is going to refract just like the light that's coming back the other direction. So what should you do this time? I think I heard the right answer out there somewhere. So yeah, roughly speaking, of course, it looks like the laser gun's being held a little off from that direction. But you can imagine it's going to do the exact same thing. And, well, that's the way to shoot it, okay? You could shoot back exactly along the path that the light from the fish comes if you want to make sure you hit it. So hold the gun, like, right in front of your eye. That just seems like a terrible idea. And then aim it right at the fish, you know, and then everything should be good. But the idea is to aim back along the line of sight. So aim directly at what you see. Use the light, okay? Questions, thoughts before we do one more slide? Anything? See, the fish questions were kind of good, huh? Yeah. Yeah. Say that again? If light comes from the fish to you along a certain path, and I shoot directly back along the same path, the light should bend exactly the same direction. So if it helps, maybe imagine that we shoot directly back this way and let it follow the exact same path. Okay? Yeah. That's the difference. So we're using a light gun instead of something physical. Okay? So finally, total internal reflection. Total internal reflection is when there is no transmission into the second substance. What we saw on side B of our example problem. Okay? What is happening? First of all, this can only occur when the light is traveling, we'll say, when from higher to lower index of refraction. Remember on that other problem, the light was trying to get from the glass out into the air, from higher to lower index of refraction. That's the only time it can occur. We know that when this happens, it will bend away from the normal. And we're going to look at kind of an extreme case of this occurring. So take a look at part A below. This is the case where I have a relatively small angle of incidence. But notice, theta 2 is bigger than theta 1. Okay? If I go over to a larger angle of incidence, notice now theta 1 has gotten a little bit bigger. Notice what happens to theta 2. Theta 2 is now even farther from the normal. Okay? So essentially what we're doing is we're taking this initial beam of light and we're just going to bend it farther and farther this direction and make it a larger and larger angle of incidence. As I do that, theta 2 is getting bigger and bigger. Got it so far? You might imagine a case where I make theta 1 so big that this bent light beam actually has a theta 2 that's 90 degrees. That's all the way bent down to the surface. Got that? All right, so we keep increasing the angle of incidence until theta 2 gets so big that it's reached 90 degrees or even larger. Okay? So what we're going to do is see how Snell's law predicts something like this. So let's start with Ni sine theta I equals Nt sine theta t. Total internal reflection occurs when theta t, the transmission angle, has hit 90 degrees. That's like the cutoff point. At that point, nothing is actually making it into the air. At best, it's sort of going right along the surface of the water or whatever that first material is, okay? So we'll say, let's let theta t equal 90 degrees. And plug that in up there. What's the sine of 90? It's 1. So that whole thing is going to become 1. And then I can solve it for what the theta initial, for theta incident needs to be for that to happen. Okay, so let's solve this for theta I at this point. So sine theta I equals nt over ni. So theta I is going to be the inverse sine of nt over ni. This we could say is the angle of incidence where total internal reflection begins. Because now the transmission angle is 90 degrees. So, this has a name. It is called the critical angle. Which I got to say sounds more dire than it actually is. We're just talking about light reflecting and whether or not it goes into the second material. It's not all that serious. The critical angle. I feel like things are going to die if this doesn't work, if I don't choose the right angle. So theta c, the critical angle, is any angle greater than or equal to sine theta 1 of nt over ni. Let's take that equation and go back to the problem we were working. And this will be the last thing that we do. So let's go back here. Make a little box. So theta c is greater than or equal to sine theta 1 nt over ni. So let's take a look at what these values were. The transmission was into air, and we had glass with 1.69. So what do you get for this angle? Inverse sine of 1 over 1.69. Once again, I don't think I'm going to wait. As soon as I find the answer, I'm telling you what it is. Should be 36.3 degrees. So if I have an angle of incidence that's at least that, then it's going to total internal reflect. What was my angle of incidence back up there? Theta 4? Ooh, it was 71 degrees. We could have done this calculation at the beginning and said, uh-oh, too much angle at that side, it's just going to bounce, and let's not even worry about Snell's law, okay? And we could just check that as it tries to get out on side B, and again as it tries to get out on side C, and then we'd know whether we need to do the calculation or whether just use the law of reflection. Sound good? Total internal reflection is pretty cool. Where is this used all the time? Yeah? Inside of waves. So you only see, what do you see? I'll have to look these pictures up. Yeah? You have something? Fiber optic cables. Yeah. The modern internet, the backbone of the modern internet is driven by light waves that are traveling down cables made of roughly glass, some type of a bendable plastic that has a higher index of refraction than air. So when I send something down a cable like that, I don't have to worry about it, say, being perfectly directed down the cable. And I could even bend the cable, right? And all it's going to do is like the beam of light will just sort of bounce around in there, but never make its way out into the air. Even if the cable bends, the same thing keeps happening, which is kind of awesome. So if you ever have a fiber optic connection in your home and it says something like, don't crimp the cable or like bend it all the way in half, like usually they have some recommendation like it's okay for the cable to curve, but be a little careful with the cable. Like, follow that recommendation. Don't be like, ooh, I know what I'm going to do. I'm going to, like, tie it up in a little knot because I want to, like, put a twist tie around it and tuck it in the corner. Like, no, follow the directions or your fiber optic connection's not going to work anymore. And that'd be sad because it's fast and nice. And I'm done. That's it.